Today we are focusing on four critical pillars: pressure drop, voidage, permeability, and effect of fines. Our objective is to provide a practical understanding for operator to manage gas flow more effectively. Now question arises that why all these matters? Simply put, a blast furnace is a gas reactor. For it to function, gas must flow smoothly upward through a body. If the gas flow is poor, your pressure drop will spike, wind acceptance will drop, and your overall production will suffer. So, these will be the consequences. Inside the furnace, we have what is called packed bed. This is the structure formed by our bottom material: coke, sinter, pellet, lampur. The key is that gas doesn't move through this solid. It flows upward through the empty spaces or voids between them. So we measure these spaces using the void fraction, which is generally denoted by epsilon in the most of the documents and books, which is the ratio of empty space to total volume. Typically, this value stays between 0.35 to 0.45. If this number drops, resistance increases, which immediately pushes your pressure drop delta P to a higher level. Next, let us define permeability represented by K. This is essentially the ease with which gas flows through the body. High permeability means your gases is flowing easily, which is good. Low permeability means the gases is struggling to pass through, which is a problem. Pressure drop or delta P is the difference between the pressure at the bottom and the top of the furnace. It is one of your most important health indicator. The more resistance of the gas faces, the higher delta P trends, which shows the graphical trend will climb up. So there is a very sensitive mathematical relationship here. K value is directly proportional to epsilon cube divided by 1 minus epsilon square. Because of this cubic relationship, even a small drop in voidage causes a massive disproportionate drop in permeability. To put all in a terms of mathematics perspective, if your void drops from zero point 0.4 to just 0.30, this is a very teeny drop if we talk in terms of mathematical numbers, 0.40 to 0.30. Your permeability doesn't just dip, it plummets by 58%. 58%. This shows how critical it is to maintain those empty spaces. Now, particle size is a major factor in the permeability. Large particles create larger void and lower dP. Conversely, a smaller particles pack together tightly, creating teeny voids that offer much higher resistance to the gas flow. The key to a stable furnace is uniform particle size. When the material are consistent in size, the gas flow remains predictable and the furnace operation stays smooth. Then we can see that the pressure drop is stable, volume acceptance of the furnace is stable over the shifts. So this is why the fines are the enemy. Small particles fill up the voids between the larger particles, drastically reducing voidage that we have seen already in the earlier slide. This leads to operational headaches like hanging, sleeping, and irregular gas flow pattern also. Now, the gas flow law states that the pressure drop is inversely proportional to a square of the particle size, and this means your particle size is cut in half, your delta P increased by 4 times. This is why size control is absolutely critical. Now, not all layers are equal. The coke layer provides a high permeability, acting as a furnace lung. The ore layer typically offers high resistance. If your coke has poor strength and break down into fines, your permeability will vanish. So, what happens if we lose permeability? So first wind acceptance drop, then two-year pressure rises, ultimately your productivity decreases and your coke rate increases, making the process less efficient and more expensive. So as an operator, you must constantly monitor delta P trends, wind volume and top temperature pattern. Common culprits for poor permeability include high center fines, poor coke strength, which includes especially micron 10 values, or improper burden distributions. So, to improve, we must reduce fines at the source, the through better screening and maintain high cook quality. Remember, this message about controlling the size to control the voidage is a key, and control voidage to control permeability is also very important, because once the sizes are getting controlled, then automatically permeability will be better. A stable permeability is the foundation of a stable furnace. So we need to control the granulometry very religiously to obtain the maximum results.